In this example, we got a particle P, which is constrained to be moving along the smooth guide. We don't really know the shape of the guide, but we do know it's smooth, and we know that the P starts out from rest there at the top. It slides down the guide. It then impacts a block A, which is at rest. We know that when the impact occurs, then A and P then stick together. They move onward then to the right to the point where what we want to find is the maximum deflection of that spring after the impact occurs. We need to break this up into several time intervals because we want to take advantage of conservation of momentum and energy the best that we can. We can't use energy all the way through because we know that during impact energy is lost. Okay, so if I break this up into time 1 to time 2, this takes us up to impact. And then from 2 to 3, that's the time during which impact occurs. And then from time 3 to time 4 will denote the time of after impact. And the reason, again, for breaking this up is that between 1 and 2, energy is conserved. For P. Okay, so we have that T1 plus V1 is equal to T2 plus V2. I'm going to choose my datum position here at the bottom for that. So with that choice, then V2 is a 0. Since it starts out from rest, T1 is a 0. If I call the 10 feet through which that ball drops in a vertical direction, if I call that H, then I have MP GH is equal to 1/2 MP VP 2 squared. So energy is conserved, and so what we find from here is that VP2 is the square root of 2GH. Okay. Now between 2 and 3. Two and 3, when I look at P and A together here, since I'm treating them together, that impact force is an internal force. So because of that, I can say that the net force on the system of A plus P, that force is a 0. So the linear momentum is conserved. So MP VB2 plus MA VA2 is equal to MP VP3 plus MA VA3. Well, A is at rest when P hits A. After impact, they stick. So this becomes MP plus MA V3. And that is just because they stick. Since they both have the same speed, I can combine the two masses together. So then I get that V3, that's the speed of A and or P, that becomes the mass of P divided by total mass of MA plus MP times VP2, and that's the square root of 2GH. So this is what's going on with A and P once they stick right after impact occurs. Now when we're looking at 3 and 4, between times 3 and 4, we're back to energy conserved. We couldn't do conservation of energy during impact because we know when impact occurs, energy is not conserved. But once we move through it, we can come back to that, and we can say that the kinetic energy before, which was 1/2 ma plus mp v3 squared, that's equal to 1/2 k delta squared. So in order then to find the compression of that spring, we just say that delta then is equal to ma plus mp divided by k with the square root times v3, and v3 was mp divided by ma plus mp square root of 2gh. So I think the key thought to have on this problem occurred right at the beginning. We want to find out for a given potential energy at the beginning what sort of the potential energy is at the end. Energy is not conserved all the way through from 1 to 4. It's conserved from 1 to 2 and from 3 to 4. But between 2 and 3, it's not. So we use the conservation to find the speed of P right before it hits. We use conservation of linear momentum during impact and use the fact that they stick to find the speed of A and P together after that occurs. And then we jump back and use conservation of energy after that. A and P are moving together. They have a combined mass of Ma plus MP. And we use this equation from which we can solve for the deflection of that spring.